Okay, so I'll get started here. So the first class was last Friday, and I think there was some like technical difficulty, so like no one got in. So we basically made a Google Classroom, Austin and I, where you can access the calculus materials, and I'll enter it into the chat right now, the classroom code. And basically just go to Google Classroom, take a few moments, um, hit join class, and then enter that code, and you should be in the calculus um, web page. So the first class is recordings, and the slides are on that, and I think they're also on the Michigan All-Stars website. And last class we talked about derivatives, and today we're going to be going off of that and exploring more concepts about derivatives. So for warm up, we're going to do these problems. You should have learned these last class. So the first problem wants us to take the derivative of 3x cubed plus 5x squared plus 7x plus 21. And by the sum rule, the derivative of a sum is the sum of the individual terms' derivatives. So you can write this as the derivative of 3x cubed plus the derivative of 5x squared plus the derivative of 7x plus the derivative of 21. And we can compute these individually and just sum up the terms. So to find the derivatives, all we have to do is use power rule. So you multiply the exponent to the coefficient and then subtract 1 from the exponent. And when we do this, we get 3 times 3, 9x squared, plus 5 times 2, 10x, plus 7. And then the derivative of a constant is just 0. So this is the derivative that we end up with. And for the second one, we're going to need to use chain rule. So you use chain rule when it's like a function inside of a function, basically. So in this, the outer function would be f of n equals 2n cubed, and the inner function would be n equals 5x minus 2. And when you substitute in n, you get the original problem. And basically what you do is you take the derivative of the outside function, which is this thing, and you just use power rule. So then it's 6 times 5x minus 2 squared, and you multiply it by the derivative of the inner function, which is this, 5x minus 2. And then the derivative of 5x minus 2 is just 5, and you end up with this thing. Okay, two more warm-up problems. So for this one, you use product rule, which states that the derivative of a product of functions is the derivative of the first one times the second one plus the derivative of the second one times the first one. It looks like this. So f of x times g of x. The derivative of that is f prime times g plus g prime times f. And f prime and g prime are just the derivative of f and g respectively. It's kind of like shorthand. And when you use it for this problem, you get the first function's derivative times times the second function plus the second function's derivative times the first function. Okay, and then when you do this, you just get the derivative of the first function, x cubed minus 5, is just 3x squared. And the derivative of the second function, 2x to the 5 plus 6x minus 8, is just 10x to the 4 plus 6. And yeah, that's basically it. And for this second problem, you use something called quotient rule, which states that the derivative of a quotient of functions is just the derivative of the bottom function, or no, just the bottom function times the derivative of the top minus the derivative of the bottom function times the top function, all over the bottom function squared. Okay, and you just basically do it for this one. So the bottom function is 2x to the 7 minus 3 times the derivative of the top one, which is 4x cubed plus 7, and then minus derivative of the bottom function, 14x to the 6 times the top function, x to the 4 plus 7x, and then divided by 2x to the 7 minus 3 whole squared. Yeah, and then if you want to find the derivative of it at a certain point, all you do is plug in x. So now we're moving on to new material. Now we're going to take the derivative of various trigonometric functions. So first you have derivative of sine x is cosine x, derivative of cosine x is negative sine x, derivative of secant x is secant x times tangent, and derivative of cosecant x is negative cosecant cotangent. Derivative of tangent x is secant squared x, and derivative of cotangent is negative cosecant squared. So you start to notice a pattern here. So sine and cosine. So sine is cosine and cosine is negative sine. And then all three of these functions are negative. Negative sine, negative cosecant squared. And then, yeah, that's basically it. So you can prove all of these functions, but just for the sake of time, I'm going to prove sine and tangent. So basically, you guys learned about the definition of a derivative last class, and to prove a derivative like formula, all you do is use that specific definition of a derivative. So the definition of a derivative states that the derivative of a function f is the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x, so all over h. And so this works because if you have a random graph like f, and then you want to find the slope at a point x comma y, and let's say you take another point here. This is x plus h comma f of x plus h. Okay, so when you draw this line here, that's a secant line that intersects the graph, and so to find the slope of this line, you do rise over run, which is f of x plus h minus y, which is f of x, and then run is just x plus h minus x, which is h, and that's how you get this thing over here. And then limit as h approaches 0. As h gets smaller and smaller, the second point here becomes nearer and nearer to the first point. So basically, you started off with something like this, and then as h gets smaller, the distance gets smaller and smaller until you're left with the tangent line, and that's what the derivative is. So using this, you can prove many trigonometric identities. So for cosine or for sine, you do derivative of sine x. It's a limit as h approaches 0. Sine of x plus h minus sine x over h. And using the sine of a plus b formula, you can expand sine of x plus h to get sine x cosine h plus cosine x sine h minus sine x over h. And using this, you can factor out a negative sine x from this term and this term here, and you're left with negative sine x 1 minus cosine h over h plus cosine x sine h over h. These are both limit as h approaches 0. And when you compute this, you get the limit as h approaches 0 of this is 0, and then this is 1. So you got negative sine x times 0 plus cosine x times 1, and then this term cancels, and you're left with the derivative of sine x is cosine. And you can do the same thing with derivative of cosine x. You just follow the definition of a derivative, and you'll end up with negative sine x. So now let me do a derivative of tangent x. So you could proceed about this the same way as derivative of sine x by just using the definition of a derivative formula. But it's much easier to think of tangent x as sine over cosine. And then this just becomes a trivial quotient formula. So all you do is cosine x times the derivative of sine x minus sine x times the derivative of cosine x over the denominator squared, cosine x squared. And when you actually plug in the derivatives, you get cosine x times cosine x, so cosine squared x, minus sine x times negative sine x, which is plus sine squared x, over cosine squared x. And then by the Pythagorean identity, sine squared plus cosine squared is 1, you end up with 1 over cosine squared x, which is equivalent to secant squared x, and we're done. So with cotangent, all you do is use cosine over sine, and for secant and cosecant, you could use definition of a derivative again, or you could think of cosecant as 1 over sine and secant as 1 over cosine. And then this just becomes another quotient rule application. So that's how you prove the trigonometry derivatives. So now we're going to move on to implicit differentiation. So like the warm-up and the trigonometry derivatives were all derivatives with respect to x of some expression in terms of x. So what I mean by that is we did like derivative with respect to x, like here, right, respect to x, and then this was all in terms of x. But now we're going to see what happens when we do derivative with respect to x, d over dx, of something that has like some y terms in it as well. And an easy way to think about this is just as another chain rule problem. So if you think about it as f of x equals x squared plus 2y, and then you let x equals y, then you end up with this. So by chain rule, the outer function is this, and then the inner function is this. So when we differentiate that, we take the derivative of the outer function and then multiply it with the derivative of the inner function. But before we do that, we can just split this up into two separate mini problems, the derivative of y squared and the derivative of 2y. So we get derivative of y squared plus the derivative of 2y, and this ends up being the first one, outer function is x squared, and then the inner function is x equals y. The derivative of x squared is just 2x, so then it's 2y times y prime, and the second one, it's just 2y prime. Yeah. And then the second one, we can do the same thing, split it up again. So the first mini problem becomes the derivative of x squared, and then you add it to the derivative of y squared. So the first mini problem, it's just 2x, some trivial power rule, and for this we need to use implicit differentiation again. So we take the derivative of the outer function, so that's 2y, and then multiply it with the derivative of the inner function, which is just y, so y prime. And yeah, that's basically it. So now we're going to move on to some inverse trig derivatives. So the first one you see here, derivative of sine inverse, is 1 over square root of 1 minus x squared. And then the second one, it's derivative of tan inverse, which is 1 over 1 plus x squared. And then secant inverse is 1 over absolute value of x times the square root of x squared minus 1. So like, that's a lot, right? That's a lot to remember. So instead of remembering all 6 formulas, all you have to do is remember these 3, because cosine inverse is just negative of the derivative of sine inverse. Cotangent inverse is just the derivative, it's just the negative of the derivative of tan inverse. And the derivative of cosecant inverse, it's just the negative of the derivative of secant inverse. So we can prove these as well. So to prove this, we use some implicit differentiation. So let there be an equation y equals sine inverse of x. So by definition, this means that sine y is equal to x. And then we can take the derivative of both sides. And when we do that, we get, so the right hand side is simply 1, because the derivative of x is just 1. And then the left hand side is a implicit differentiation problem, where the outer function is sine and the inner function is y. So when we do this, we get derivative of outer function, cosine y, times the derivative of the inner function. So it's y prime. And we want to figure out what y prime is, right? Because dy over dx is the derivative of inverse sine. And y prime is just another way of writing dy over dx. So we want to solve for this. So we get that y prime is 1 over cosine y. And by the Pythagorean identity, we know that sine squared plus cosine squared is 1. So we can rewrite cosine y as 1 over the square root of 1 minus sine squared y. And then from up here, we know that sine y is x. So we just substitute. We get 1 over square root of 1 minus x squared, and we're done. So for the other like inverse trig functions, you could go through the same process as well. It's not too difficult, but it's also much easier to realize that for these three functions here, it's easier to realize a relationship that cosine inverse shares with sine inverse, cotangent inverse shares with tan inverse, and so on. So if you look at the graph of inverse sine, inverse cosine, and the other inverse trig functions, you realize that arc cosine is just pi over 2 minus sine inverse of x. And arc cotangent is pi over 2 minus arctan of x. And once you realize these relationships, it becomes much easier. So cosine inverse x is pi over 2 minus sine inverse x, for example. And when you take the derivative of this, you get the derivative of inverse cosine is the derivative of pi over 2, which is just a constant, so it's 0, minus the derivative of sine inverse x, and you end up with the fact that derivative of cosine inverse is negative derivative of sine inverse. And you can just do that for the rest of the functions here. So now let's move on to logarithms. So the derivative of a to the x is a to the x ln a, and derivative of log base a of x is 1 over x times natural log of a. So all you have to do to prove these is use the definition of a derivative again, and use some like log properties, exponent properties, and it's pretty trivial to prove these. But one thing I like to look at is some special cases, like what happens when when a equals e, right? So a equals e. You let it be e. then you end up with the fact that the derivative of e to the x is just e to the x times ln e, and ln e is log base e of e, which is just 1. And same thing with this, the derivative of log base e of x, which is the derivative of ln x, equals 1 over x times ln e, which is just 1, so you end up with 1 over x. So that's all there is to logarithms. Now we're going to look at some application problems. So a small balloon is released at a point 150 feet from an observer who is on level ground. If the balloon goes straight up at a rate of 8 feet per second, how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? So to do this, let's first draw a picture. So there's this guy standing here, and then a balloon is released at this point 150 feet away, and then there's a balloon that's going up, and then you want the rate of increase of the distance from the observer to the balloon, and let's call this the height of the balloon x and the distance from the observer to the balloon y. So we're given that the balloon goes up at a rate of 8 feet per second, and with that we can conclude that dx over dt is 8 feet per second. And notice now that I'm taking it with respect to time instead of just x. We're getting more specific here when we do it with respect to time. And you want to figure out dy over dt, which is the rate of increase of this. Okay, so when you're given these problems, you want to basically write down all of the information you know, and then try to come up with an equation that you can differentiate and substitute this in to basically get what you're looking for. So right now we know that this is a right triangle. So what we do is we use Pythagorean theorem, which states that 150 squared plus x squared equals y squared. And now we differentiate this with respect to t. And 150 squared is just a big constant, and the derivative of a constant is 0. So we end up with 0 plus 2x times dx dt, because this is once again implicit differentiation, where what you're differentiating with respect to and the actual terms in the equation are not the same. So, and then this is equal to 2y times dy dt, and then we know that dx dt is 8, so this is 8. And then we also know that they're asking when the balloon is 50 feet high. So we know that we want to figure out dy dt when x equals 50. So x equals 50, so then this is 50. So then 2 times 50 times 8, that's 800. Let me go here. So then we know that 800 equals 2 times y, which is y, which is 150 square root of 150 squared plus 50 squared by Pythagorean theorem here. Alright, 2 times square root of 50 squared plus 150 squared times dy dt. When you multiply it by dy dt. And then you want to figure out dy dt, so all you do is divide, and then you get that the rate of change from the observer to the balloon when the balloon is 50 feet high is 400 over square root of 50 squared plus 150 squared feet per second. So that's basically how you do this problem. And we're going to look at another example here, which says a particle moves along the x-axis. So this is like 1D motion basically. There's just a particle. And then you're given this function which states its position given a time t. So let this be like the 0 mark on the x-axis, let's say. So the time at t equals 0, the position is going to be at -1, so it's going to move there. And then at time t equals 1, it's going to be 4 minus 18 plus 15 minus 1, which is 0, so it's going to move back, and it's just going to move back and forth at different times. And there's actually a lot of stuff we can do with this one position equation. So given a position, this is like basic physics stuff, I guess, but not really. But like given this position function, we can differentiate with respect to t with both on both sides, and then we get that dx over dt it's just a power rule, so it's 12t squared minus 36t plus 15, and we can this turns out to be the velocity function, because when you take the derivative of a position function you get velocity, and we can actually differentiate this again to get 24t minus 36 equals dv over dt, which turns out to be acceleration, or the acceleration function. So when you get this, when you get the position function, you can figure out a lot of things about velocity and acceleration as well. And let's look at like the graphs of these. So 12t squared minus 36t. So 12t squared minus 36x, what was it? Minus 36x plus 15. So it's just a quadratic equation. And when you look at this graph, you see that at time, and we don't care about like when it's before time t equals 0, we don't care about this part because it specifically says when t is greater than or equal to 0, and in the context of the problem it doesn't really make sense when time is negative. So at time t equals 1.5, we realize that the derivative or the slope of the tangent line is 0, which means that the acceleration basically switches from velocity decreasing to velocity increasing, and at this specific point the acceleration changes sign, yeah. And at these 2 points, the roots of the quadratic function, 0.5 and 2.5, velocity is 0, and it goes from velocity positive to negative, and then negative to positive. And from there, you can conclude that acceleration reverses direction. And when we look at let's look at speed. The speed. Okay, so velocity is like the speed and the direction. So it's like if it's negative, it's like left, and then if it's positive, it's right. But speed is just the speed portion of velocity. So what we can do is just take the absolute value of velocity, and you get this thing here, which is just the velocity function, but all positive. Okay, and let me graph the position function. So 4t cubed minus 18t squared plus 15t minus 1. So you get this thing here. So you care about the points that are greater than 0, and you find out that 0.5 and 2.5 are relative extrema on this graph. So and if you remember from earlier on the velocity graph, points 0.5 and 2.5, that's where it like reverse direction the particle, and it's like pretty obvious here, right? Because it goes from like 0.073 to 2.5, and then it starts decreasing again, so it starts moving in the opposite direction, and then once it reaches 2.5, it reverses direction again and begins to go to the right. And 1 and 3.427, it's basically when it goes from the positive side of the x-axis to the negative, and the negative to the positive. So by looking at these graphs, it actually tells you a lot about the like trajectory of the particle, I suppose. And let's see. Okay, so you can also see when the particle speeds up and slows down. So when the particle speeds up, the acceleration is positive and the velocity is positive, or the acceleration is negative and the velocity is negative. And when it slows down, the acceleration is positive and velocity is negative, or the velocity is positive and acceleration is negative. And this is talking about speed, right? So you want like you don't care about which direction the particle is moving in. You only care about um, like the absolute value of the velocity. So when acceleration and velocity have the same sign, um, I guess you can think of it as the velocity is um, going in the same direction as it's accelerating, so it's going to be speeding up. And same with when they're both negative. When they're both negative, it's still going in the same direction as the acceleration. But when it slows down, it's kind of like they're acting against each other. Like velocity goes in one direction and then acceleration in the other. So it like uh, uh, causes it to slow down. The speed starts to go down. And then when the velocity is positive and the acceleration is negative, uh, it's the same thing. It just starts to slow down because they're acting against each other. Um, that's basically it for this class. So for the people that like dropped in later, make sure to join the Google Classroom. I put it in the chat. I'll do it again. Um, just head on over to Google Classroom and enter in this code, and you should be able to see this class's recording, this class's slides, and last class's recordings and last class's slides. Yeah, um, and that's where we'll make any announcements and stuff. So yeah, make sure you guys copied that, and I guess that's it.